Hello there, AP Environmental Science class. Okay, we're moving on now to Chapter 5, which talks about climate and terrestrial biodiversity. Once again, there are about 59 slides to this lesson, so I'll be splitting it up into Part 1 and Part 2. All right, so and basically in Part 1, we're going to talk about climate and weather, and then in Part 2, we'll talk more about how that affects the terrestrial biodiversity of an area. So we start off with a core case study talking about the African savanna. Why do grasslands grow in some areas while forests and deserts form in others? Well, the answer to that question, guys, is climate. Climate is the long-term conditions, atmospheric conditions of a particular area, mainly looking at the temperature and the precipitation of a particular area. So climate could be tropical, very warm, very moist, could be polar, very cold, very dry, or could be temperate like we are here in Ardsley, little warm, little cold, little dry, little wet type of climate. But the climate is going to determine what type of biodiversity you have on land, okay? Because that climate is going to be important. And again, what's the difference between climate and weather? Weather is going to be what's occurring over the next couple of hours, the next couple of days, while climate is going to be, again, long-term, months to years, okay, what's going on in a particular area. So in a savanna, you have scattered trees with warm temperatures and actually not that much rain. So it's not as dry as a desert, but it's definitely drier than we are here in Ardsley on a savanna. What we're seeing, though, is the savannas are being lost, and as a result, the loss of those savanna habitats are threatening native animals like the African elephant that we see right here. So again, we'll talk more about these biomes as we go through the next couple of chapters. All right, so first off, we're going to talk about weather. Again, what factors influence weather. So weather is the set of physical conditions of the lower atmosphere in an area over a period of hours to days, okay? And that's the key between weather and climate. Climate is long-term, weather is short-term. And we're talking about atmospheric temperature and precipitation, all right? So how hot or cold it is, how much rain, how much snow falls, et cetera, et cetera. Weather is going to be affected by a couple of things. Number one, moving masses of warm or cold air, okay? Number two, atmospheric pressure changes, all right? That's how much air pressure is pushing down on you. And number three, by the occasional shifts in the major winds that we have a global wind pattern here on planet Earth. So we'll talk about these three in more detail as we now go through the next couple of slides. So first off, we're going to talk about weather being affected by those moving masses of warm or cold air, and those moving masses of warm and cold air basically come together along something that is called a front. A front is a boundary between two air masses with different temperatures and densities. Why densities? Well, if you remember back to Earth science, warm air is less dense than cold air, right? So a cold air mass would have more dense air than a warmer air mass. In addition, moist air is less dense than dry air. So again, these are your different air masses, and in that boundary, we have a front. Very similar if any of you guys are into history, right, or into the military, right? What do we say? There's a front, right? That's where the battle takes place, right along the front, the boundary between two different armies. Well, same thing in weather. It's just instead of armies, we're talking about two different air masses. There are a bunch of different types of fronts. We're only going to really need to concern ourselves with two in this class. One is the warm front, which is when warm air replaces cold air. So in a warm front, the advancing warm air mass rises up over the cooler air. Moisture begins to condense into clouds, and you have layers of clouds at different altitudes. And usually with a warm front, you kind of have a long period of mainly light precipitation, either rain or snow. Next type of front is a cold front. A cold front is when cold air moves into warm air. But because the cold air is more dense, the cold air mass stays close to the ground, causing the warm air mass to be pushed higher in the sky very rapidly, and that produces rapidly moving towering clouds called thunderheads or cumulonimbus clouds. These can cause your high surface winds and thunderstorms. So usually cold fronts have quick moving heavy rain or thunder showers, while your warm fronts usually have steadier, lighter precipitation that goes on for a longer period of time. So here are basically your cross sections of a warm front on the left and a cold front on the right. Once again, in a warm front, the warm air slowly gradually rises up over the cold air mass that is at the surface, because again, cold air is more dense, warm air is less dense, so it rises, okay? And that produces this large area here where you have clouds, and again, usually a light, steady precipitation, either rain or snow. In the cold front, you have this cold air mass that's close to the ground, shunting or pushing up the warmer air mass very violently, very quickly out ahead of the cold front, and so what does that happen? That usually produces this area where you just, not a broad area of clouds, a very narrow area of clouds, but this is your thunderstorms. These are your heavy rain showers, usually occurring with a cold front. Okay, so those are the differences. Warm, cold front, definitely understand the differences between the two. Okay, weather is also affected by atmospheric pressure and wind patterns. So, what is atmospheric pressure? Well, it's just that. It's the amount of atmosphere or the pressure of the atmosphere pushing down on you. So that would make the most sense, right? That we would have the greatest amount of atmospheric pressure near Earth's surface, right? Because you have the entire atmosphere pushing down on you. If you climb up to the top of Mount Everest, okay, a lot of the atmosphere is below you, right? So you don't have as much pushing down on you. So your atmospheric pressure is actually a little lower on the top of Mount Everest than it is here in Ardsley, closer to sea level. In addition, we talked about previously, high pressure contains cool, dense air, while low pressure usually contains low density, warm air. And that air rises, expands, and it cools. So remember back to earth science. As air rises, it expands and it cools to the dew point. Once the temperature and the dew point are equal, you have a relative humidity of 100%, and then clouds begin to form, and then in most cases, some type of precipitation will follow thereafter. Okay, so that's basically how it works. Now, we also have the jet stream, and again, you're thinking back to your earth science days, which is powerful winds at about 30 to 35,000 feet in the air that actually circle the globe and drive our weather systems around the earth. So the jet stream is what kind of drives these air masses, these low pressure, high pressure, these fronts around the earth. We also have something that we need to talk about, ENSO, the El Nino Southern Oscillation. So I'm sure many of you have heard of El Nino, all right? These are conditions that usually cause us here in Ardsley to have a wet and warm winters, all right? But what is ENSO? It's the periodic change in wind patterns in the Pacific Ocean. This results in drier weather in some areas and wetter weather in others. And this can alter weather conditions over 2/3 of the globe. So let's talk about this because you will need to have a general understanding of what causes El Nino conditions. So in normal times, okay, what we have here, this is the Pacific Ocean, okay? Here is South America and here is Australia. So in normal times, what we have is we have lower pressure that is more towards Australia. That causes the surface winds to blow westward, okay? So from South America, the winds blow towards Australia. Okay, this causes rain in Australia, and it causes warmer water to be pushed westward. So what that actually happens, what then occurs is that colder water ends up upwelling or coming up from the deep ocean and sits off the coast of South America right here. Okay, this is what happens normally. All right, and this is, the normal conditions. All right, warm water gets pushed westward, cold water upwells off the coast of South America, and that's basically normal. In El Nino conditions, what happens is the lower pressure that's near Australia kind of dies out a little bit or shifts a little further to the east. That causes the westerly winds here, the westerly trade winds, the surface winds that blow westward to actually get weaker or even die out altogether. So what happens? Think about it. Wind was blowing west, pushing all this warmer water to Australia. What happens when the wind stops? Well, that warmer water actually flows back towards the coast of South America. So what happens is you have now in an El Nino condition, you have warmer water off the coast of South America than you would normally have. This now causes the wind patterns, the jet streams across the entire Earth to shift, and this tends to bring in, especially for us, warmer and wetter conditions. And it makes kind of sense, right? Because if you have warmer water here in South America, as these low pressure systems move from east to west, they bring some of that warmer conditions up into our area, and that's why we're usually warmer and wetter in an El Nino year. If you're curious as to where that term came from, El Nino, and El Nino is baby in Spanish, and how this term came to be is that about 100 years ago or 200 years ago, fishermen off the coast of South America basically fish for anchovies, and anchovies need cold weather. And what these fishermen noticed, even not 100, 200 years ago, over the course of how long they've lived there, is that every now and then the water would get warmer and all the anchovies would die, and unfortunately many people would lose their lives from starvation. It usually happened right around Christmas. So for those of you who are Catholic, Christmas is a holiday that celebrates the birth of Jesus, a baby, and South American people are mostly Catholic, and so they dubbed this phenomena that they experienced El Nino, or the baby after the Christ child that was born on December 25th, because usually they saw this pattern beginning around December. So that's where the term El Nino comes from, and it's basically when warmer water shows up off the coast of South America that killed the anchovies. That's where the term came from, but because that warmer water shows up here where normally it's colder water off South America, the west coast of South America, that of course then changes the weather pattern. So that's what we're talking about when we talk about El Nino and ENSO. All right, so definitely have an understanding of what these conditions do, and also have a general understanding. Here is where this is the change, okay, in what you get. So again, you'll notice up by us here, unusually warmer periods. You'll notice unusually higher rainfall in the southern United States, okay? You'll notice drought occurs in Australia and in parts of Indonesia. You'll notice Japan, Southeast Asia gets very warm. So these are the effects of El Nino. So again, just you don't have to memorize this per se, but definitely understand one or two of the effects that El Nino has on global circulation and on global climate. Okay, moving on. Tornadoes and tropical cyclones are violent weather extremes. So we'll talk a little bit about tornadoes, and another word for tropical cyclones would be hurricanes. Tornadoes, violent weather events that form over land. Vertical convection currents suck air upward, and most occur in the American Midwest in spring, known as Tornado Alley, all right, Oklahoma, Kansas. Actually, in the entire world, the greatest amounts of tornadoes occur right there in the middle portions of the United States. That's where most of your tornadoes occur. There's a little peak in the Germany, Austria area of Europe as well, but most tornadoes on this planet occur in Tornado Alley, in the American Midwest, and usually they occur in the spring. Tropical cyclones, again, these are your hurricanes, your tropical storms. They form over warm ocean water. So tornadoes and hurricanes form in completely different ways. Okay, tornadoes are over land and they occur with thunderstorms. Hurricanes and tropical storms occur over warm ocean waters. They take a long time to form and gauge strength, but their intensities are rated based on their wind speeds. Hurricanes are much larger than tornadoes. Hurricanes, as I'm sure you know, move over an area and 200, 300 miles are basically destroyed. A tornado is so tiny that you could have a tornado move through your hometown. On one side of the street, it looks like total devastation, nothing left. On the other side of the street, it looks like nothing happened. That's how crazy tornadoes are. That's how small they are in many instances. Hurricanes, obviously not the case. They are much larger. Right, so again, here's just kind of a picture of how a tornado forms. You get moist air drawn in, cool air is descending, warm air is rising, and you basically have some shear involved, and you get this twisting. And look, you're not going to have to know how these tornadoes form for this class. Just know that tornadoes, again, over land, they're going to be formed in thunderstorms, basically with rising and sinking air. All right. And again, they're small, violent, very violent. Winds are usually faster in tornadoes than in hurricanes, but they're much, much smaller. Hurricanes, very, very large, again, forming over water. Most surface winds spiral in towards the center, and then you get this rising air. Again, the center, the eye is calm. All right. It's like nothing is happening in the eye. Then right around the eye wall, that's where your strongest winds are. And again, heavy rain, very strong wind over a very large area. That's your hurricane, or otherwise known as a tropical cyclone. And again, they form over warm water. Okay, they form over warm water, and they are very, very large. Okay, so what factors influence climate? So we just kind of talked about weather. Just gave a little brief of what weather is all about, some of the terms, some of the things that you'll see. Now we're going to talk about climate. And when we talk about terrestrial biodiversity and then talk about biomes in the next couple of chapters, climate is going to be what's important in determining the type of biodiversity you get and the type of biome you get. So key factors that determine an area's climate: incoming solar energy, which is basically how much energy is coming down from the sun, the Earth's rotation, global patterns of air and water movement, atmospheric gases, and the Earth's surface features. And once again, this is kind of the executive summary. We're going to go in and talk about all these in a bit more detail over the next couple of slides. So, several factors affect regional climates: weather, temperature, precipitation, wind speed, and cloud cover. Again, hours to days. Climate is an area's general pattern of atmospheric conditions over 3 decades and longer. Again, so much longer period of time, and it varies among the Earth's different regions. All right, so here are some of your regional climates here. Okay, so this is kind of what we're looking at here when we look at some of your regional climates, and you'll notice, just kind of looking at the map, we have cool temperate climates up here. We got upwelling here that causes some cold weather. You'll notice the warm temperate climate. You'll notice the yellow is dry, right? Your Sahara Desert is right here. And again, these are some of the ocean currents that basically travel around the world's oceans. So you don't need to memorize this, but you need to understand what you're seeing and what you're reading. And again, areas near a warm current of water going to have a warmer climate than areas that are necessarily near a colder current of water. Again, that's for locations along the coast. Inland, obviously, the ocean is not going to be as big of a factor. So factors that determine regional climates: cyclical air movement driven by solar energy, uneven heating of the Earth's surface by the sun. This varies with latitude, and that produces different pressures, right? If it's hotter in one area, you're going to have lower pressure. Then in another area, it'll be higher pressure, and then air moves from high pressure to low pressure, so this causes the winds to begin to blow. Tilt of Earth's axis and resulting seasonal changes. Again, back to Earth science, think about that 23.5 degree tilt of Earth, and that causes the seasons. Rotation of Earth on its axis, and again, the ocean currents help redistribute the sun's heat. So, talking about some of these factors, this first one is basically, this is convective cells. All right, so this is what, when we talk about, this is basically showing you a sea breeze situation here. But in general, this happens around the Earth. You have lower pressure, all right? Air flows towards low pressure. Low pressure, though, air usually is hot and wet, and so it will rise. That air then condenses, forms precipitation. It flows back over the land where it's cool now and dry because there's no clouds anymore. That cool and dry air sinks. You now have high pressure, and then the air flows once again back to low pressure, and this whole convective cell is what it's called, continues, okay? So really, in general, what is a convective cell? It's warm air rising, cold air sinking somewhere else. Warm air rises, cold air sinking. So that can occur in a few miles right by the ocean, which is known as the sea breeze or land breeze effect, or this can occur over the entire globe where warm air is rising at the tropics and sinking at some other latitude. Okay, so one thing you need to know are these convective cells. Again, warm air rising, cold air sinking. Next thing are these are your global air circulation patterns, okay? So what you need to know here is that you have what are known as these Hadley cells of air that are basically going up and down. So you'll notice rising air at the equator, sinking air at 30 degrees. You have sinking air at 30 degrees latitude, rising air at 60, and then you once again have sinking air at the 90 degree at the North Pole, and then you do the same thing in the southern hemisphere as well. Again, this is back to your earth science days, okay? And then depending on where the air is rising and sinking will determine the climate. So what did we say? Rising air, right? Usually warm, usually moist, usually causes rain. So look here, see where the air is rising here, you have tropical rainforest, you have tropical deciduous forests where you need heat, you need moisture, right? Look at where the air is sinking. What did we say? Sinking air dries things out, higher pressure. Look at where your deserts are, right where the air is sinking, right? Then you have rising air again at the northern latitudes, like where we are. You get more forest because you need more moisture, right, to produce big trees. You need a lot of rain. We're going to talk about that more in a couple of chapters. And then at the North and South Pole, right, it's very dry, cold deserts because that air is sinking. Okay, so that's very important. These Hadley cells, rising and sinking air over large areas, produce climate that obviously then produce the biodiversity that you'll get, right? Different diversity in a desert than you're going to get in a tropical rainforest, okay? Same thing with the Earth's tilt. Remember, the highest solar energy input is at the equator where you have a 90-degree angle, right? From the sun's energy intercepting the Earth at a 90-degree angle. That gets the most intense sunlight that you can get. So at the equator, most of the season, it's near that 90 degree or straight up and down. Here it says 0, but it's really straight up and down, okay? And then as you go further north and south, the angle of incidence, as it's called, right? The angle that the sun's rays intercept the Earth, the angle of incidence, will actually get will change, and as it decreases from 90 degrees, the intensity of the energy gets less. And this is why it's the hottest near the equator and it's colder near the poles, because of this angle of incidence and how it changes from the sun as you go from the equator to the poles. Why does that angle of incidence change? Well, it's because of the tilt of Earth on its axis, right? Earth is tilted 23.5 degrees. So as a result, in the winter, the northern hemisphere is tilted away from the sun, and that angle of incidence is even lower, providing less solar energy. In the summer, right, us here in the northern hemisphere tilted towards the sun, and that increases our angle of incidence closer to that 90 degrees, which is the maximum, and therefore our solar energy increases, and therefore we warm up, okay? And remember, the opposite is occurring down in the southern hemisphere. So that's another reason why regional climates are affected. Again, that 23.5 degree tilt of Earth on its axis. And then finally, we have these deep and shallow ocean currents that move warm and cold water around the Earth. So again, where you're near warmer water, you're going to have a warmer climate than if you're near colder water. And so what happens is these deep and shallow ocean currents actually help redistribute heat, right? Look at that, bring hot water north. What happens when hot water gets north? It cools down, right? Moves cool water south. What happens when cool water gets south? It gets hot again, right? And moves north, et cetera, et cetera. And this also helps affect our regional climates by distributing or distributing the amount of heat on Earth, trying to distribute it more evenly around the Earth, and that obviously affects your climate as well. Okay, finally, we have these greenhouse gases that warm the lower atmosphere. What are greenhouse gases? Well, basically water, carbon dioxide, methane, and nitric oxide, okay? These are going to be your main greenhouse gases. Now, a natural greenhouse effect is actually good, and we're going to talk more about this when we do global warming. We have a whole chapter on this. This is just kind of introducing you to it, and I'll talk about this more when we get there. But believe it or not, if Earth didn't have a greenhouse effect, there would be no life on this planet because the average temperature would be around 0 degrees Fahrenheit, believe it or not. Because of our greenhouse effect, our average temperature is right around 55 degrees Fahrenheit, again, averaged over the whole Earth. And as a result, we can have life. If there was no greenhouse effect, if there were no greenhouse gases in our atmosphere, there would be no life on this planet. So we want to thank the greenhouse effect. The problem is human enhanced global warming. We are adding, especially these bottom two. Water is a greenhouse gas, but we don't add it to the atmosphere. So it's not called an anthropomorphic greenhouse gas, but these other three are, okay? And because we're putting these chemicals into the atmosphere, we have what I call a runaway greenhouse effect, or a greenhouse effect on steroids. So again, the greenhouse effect in general is good. It's this greenhouse effect on steroids that we are doing as humans because we're putting too much of these chemicals into the air, the carbon dioxide, the methane, for instance, that our global temperatures are warming. And again, much more of that when we get to that global warming section towards the end of the course. Okay, so that's going to be the end of part 1. All right, on chapter 5, climate and terrestrial biodiversity. Check back in for part 2. And as always, thanks for listening.